reporting this work to the US Forest Service and the team that's on the project from the Forest Service for really getting this work off the ground, getting it going, and letting us Brits come over to New Jersey and do some of this really cool work. Also in that vein, the New Jersey Forest Fire Service have been crucial for us in terms of getting these burns done safely and in the right conditions, and they've been really great at supporting this stuff, so thank you to them. I've also put here on this title slide the Joint Fire Science Program, and this project that we have has built on work funded by these, and I think it's great to show some of the interagency stuff that goes on and how these projects can all link together and how you can leverage from one project to the next. So I'm going to talk a little bit, first of all, about Scotland. So this is where we are. We're in Scotland, and usually when I start speaking about wildfires, the first question I ask is, you're in Scotland, it's always raining and cold, isn't it? You don't have wildfires. Well, maybe if you just walk through the next few slides, I can make a little point. So Edinburgh is here, highlighted with this little arrow, and I'm just going to put up a few instances of wildfires, and depending how well you know Scotland, these might have some significance or not. But this is a wildfire that happened right in the very north of Scotland. This is in a region called Caithness. This is almost as far north in the United Kingdom as you can get. It's almost as far north as vegetation actually grows in the UK. So there's been wildfires up there in the country. Anybody familiar with the Loch Ness Monster and Inverness? Well, this is a wildfire that happened there as well. We've had wildfires. This is an important one because where this third picture is pointing to is where all the Scotch whisky is made. So we have had wildfires in that region. And then the Isle of Skye is quite a famous landmark, and we've had wildfires there also. And finally, even in the center of our capital city, this is an extinct volcano. It's called Arthur's Seat, and we regularly have, I'll admit, quite small wildfires, but nevertheless we have burning of vegetation right close to the downtown of Edinburgh. So these are fires in the UK, so we do have a wildfire problem, if you like. And just in case anybody's thinking that I'm cherry picking these events, these all happened last month. So these all happened in the month of May 2018. And it does tell you that even though we have a lot of rain and it's very cold, wildfires are still a problem in our ecosystem. And right now we've got a very large wildfire happening just a few hours south of here in Manchester, just outside Manchester, and that's hitting the news quite hard here in the UK, and dealing with many of the same problems that we're trying to help understand on the other side of the Atlantic, looking at the impact of the fire on the population nearby, looking at air quality issues, looking at flame spread, looking at management techniques as well. So we are a little bit coming from the outside, but this is a problem that is relevant to us here in the UK as it is with you guys over in the US. So without too much more introduction, I'm going to just continue with the actual talk of what we're doing as part of this CERDEP project. But as I say, I'm on the phone, but this is work that is done really by the great team that we have here in Edinburgh. And today I'm going to speak about and present, borrow, I guess, the great work that's being done by Carlos, Eric, and Zach. Some of you might be familiar with these guys. You might have seen them around if you've tooled around a little bit over at the Silas Little Forest. These guys were out there a couple of times this year working on this project. Chris Thomas is another one of our postdocs in this group here. He didn't quite make it into this selfie, so if he's listening, I'm sorry, Chris, but you didn't quite make it on this occasion. So Carlos, Eric, and Zach have been working really hard across a number of topics that we'll delve into kind of in the second half of this presentation. But I want to make it very clear that all of the good work, all of the interesting science, it's these guys that are driving that and pushing that forward. So just to put this talk in context with the rest of this seminar, our seminar series, I think it's a great thing, talking about fine scale to big scale in the fire behaviours, and we're definitely going to be probably towards the end of this talk looking more at the fine scale than at the big scale. And I want to kind of take you on the road through that. And in the last couple of of seminars in this series. We've heard from the speakers on the two topics that are on this slide. So Mike did a really great talk on some of the fuel characterization work that's going on. And that's a really important aspect of what we're going to talk about today, and we kind of rely quite a lot on that expertise in how to characterize the fuels that we're studying. And Ken gave a great talk also on some of the meteorological side of things, some of the measurements of ambient conditions, but also of the fire-induced conditions as well. So this is great stuff. So this is what I've kind of tried to break down into quantifying the fire environment. So this kind of thing about characterizing the fuels and characterizing the weather conditions are what I would call characterizing the fire environment. Now, what we're trying to do, I should, before I move on, give this quick shout out to Professor Simeone's talk, which is happening next up in the schedule. So he's on, I think, July 11th. He's going to talk much more about the impact of some of these weather conditions and wind conditions on the burning of this vegetation. So that's just a bit of a commercial break to advertise that talk. That's going to be great to listen to. But in terms of quantifying the fire environment, I think that's something that is a work in progress very much, and as the team here is working on that. And what we're looking at doing here is quantifying a little bit more the fire behavior, and that's kind of our research question. Can we quantify the processes, the conditions, or whatever it might be that we can use to quantify the fire behavior? And I think this is something that I just want to kind of give you a quick update or a quick overview on in terms of our view of this and how we're approaching this problem, which is maybe a little bit different to what you've seen before, or different to some of the other kind of vocabulary that might be used. So this is kind of just getting everyone on the same page sort of thing. And if we go back to this picture from the title slide, I mean, there's a lot going on here in terms of the fire spread, and I've kind of thrown up a few words to try and describe things in terms of a few words that explain how we might describe some things. So we've got the meteorological conditions, so we want to know what is the wind speed, we want to know what is the humidity, all this kind of stuff. We've then got things like flame spread. Well, that's a really important thing to know if we're trying to manage the fire, or if we're trying to predict where the fire might go and allocate resources. But behind all of those things, we've also got processes like the combustion reaction. So what's actually going on there? How is the fuel decomposing thermally? How is it reacting with the oxygen? How is it burning? And that's a kind of different level of process. So you can see kind of a few of the key things going on this slide. If I advance to the next slide, which means I have to just do a quick bit of wizardry, sorry. If I advance to the next slide, hopefully you can see that I've kind of color-coded these. So these are now being grouped into some different categories. And if I just move on to the next slide, I've kind of broken these down into 4 different categories. There's what I describe as the fire environment. So those are things like the weather conditions, the condition of the fuel moisture, the fuel structure. Is it a densely packed litter layer? Is it a not so dense litter layer? Are there lots of shrubs present? Are there any ladder fuels? That sort of thing. And also the topography. What is the slope? And so on. So all those things are kind of grouped together into the fire environment and put them in that category. The next one down, we've got what I'm loosely describing as fire processes. So the fire processes are the mechanisms of heat transfer, so the conduction, the convection, radiation, and so on that might go ahead and heat the fuel that is unburned. We've then got the combustion processes. So these are things like the thermal decomposition of the fuel. How does it respond to heating? How does it break down? How does that chemistry of the fuel and the kind of chemical composition of the fuel change? And then we have things like the airflow as well. So what is happening really close to the ground where these litter layers are burning, because those are the fires that this project is really focusing on, the kind of low intensity fires where we have a high influence of the airflow at the ground level. We then need to talk a little bit about how we quantify these processes. So the processes are typically quantified in terms of the temperature evolution. So how does the temperature of a fuel element or a pine needle or a piece of the litter layer, how does that change as a function of time? We might also want to characterize the temperature evolution in the gas phase, so to try and capture the dynamics of the flames and the structure of the flames as well. We've also then got really what I think is one of the key parameters of fire safety and predicting fire behavior, which is the energy release. So how much energy is this fire releasing and how is that energy being released? That's a really crucial question for us because that determines the amount of convective energy that's there, the amount of radiative energy that's available, and lets us really understand the balance from a really thermodynamic point of view. We've then got things like the flow velocity and the heat flux. So these, again, are ways of understanding how energy is being transported from one part of the burning fuel to another. And when we put these things together, these are really what this talk is going to focus on. So as I said before, we are at the fine scale. So we're looking at really some quite small processes and how to measure them and how to quantify them at the scale of the laboratory, and I'll talk a little bit about that in the next couple of slides. At the bottom of this slide, you can see the term spread rate, and we have fire danger and ease of ignition, and these are great kind of management tools that come out of an understanding of all of these fire processes. So what we're really trying to do is to take the fire environment and the fire processes and be able to quantify them in an adequate way that we can improve the ability to predict spread rate, predict fire danger, predict the ease of ignition, or whatever kind of management tool might be relevant at the time. So hopefully that makes a bit of sense about how we're working, and just to show how this fits in with the rest of the project. Well, we've had some talks already looking at some of this stuff. Apologies if I've missed anything off of this slide, but the most recent talk I think was by Bob, and he was talking about the energy release and how we're measuring energy release radiatively, so the radiation that's coming from the flames, and using that to understand the fraction of radiative energy and convective energy from the fire. Ken did a great job talking about how we measure the meteorological conditions and also the flow velocities during the fire. So Ken's covering a lot of this stuff and diving into that data, and that's really helpful for fitting into our project and our program of work here. And Nick and Mike have been doing a lot of work characterizing fuel structures, fuel moistures, and much more beside that. So really this is a piece of work that is really closely integrated with the bigger project. The main difference is we're on one side of the Atlantic, and pretty much everyone else is on the other side. But on a scientific point of view, we're really closely integrated. Now, I've just put this a little bit in context of what we're doing in the field. So I've put some red arrows on this plot, on this picture, and hopefully they make sense to what we're doing. But I'm just going to try and walk through some of the measurements that we make in the field, because that's really important to understand what we do in the lab as well. So starting with the yellow energy release, which is right here. The energy release we're measuring in the lab by this slightly strange looking, I'm going to go a bit crazy and try and use some of the highlighting tools, but this slightly kind of crazy looking chimney thing that we've put in the woods. So we can do we can apply some theory, some equations to this, and we can actually measure how much energy is this fire giving off. What is what we might call the power of the fire, and from that we can back out things like the fire line intensity. We can make direct measurements of that, and that gives us an energy release per unit length, per meter of the fire front. So that's really cool being able to do that. In the field, we've also got these thermocouples, which are measuring temperature. I'm not sure how well this is showing up, but hopefully you can see. So these are this downwards kind of hanging things off of this truss, and there we're measuring the temperature and really being able to characterize the thermal environment around the flame front. You can't really see them here because they're embedded in the litter layer, but we've got measurements of flow velocity and also heat flux in the litter layer that we can use to understand a little bit more about the processes that are going on at the field. So this is great, and we've been doing this great work. You will have seen maybe some of it from Ken's talk and from some of the other talks. These great experimental burns on a relatively small scale in the field, but really capturing all of that complexity of the flow environment and the fuel structure and the changes in the fuel moisture spatially as well as in time. And that's really great. That really lets us understand how these fires behave and what range of conditions that we get. But because of the type of fire we're dealing with, we actually have a really great and quite unique opportunity to study this also in the lab. Now, doing wildfires in the lab normally is pretty difficult because recreating the conditions of a wildfire is not easy to do in a lab. The amount of energy that's being released from a head fire, for example, can be really enormous, and trying to understand that and reproduce it in the lab is a huge challenge. However, because these are relatively low intensity fires, the image on the left is just a crop from the previous slide, and this kind of round image in the middle, this is just a zoom in on a section of that, and we can actually take that kind of fire behavior and recreate that really quite effectively in the lab, and that's our starting point for a lot of this stuff. I think it's great that we can do this. Being able to work in the lab lets us make all the same measurements. So, as you can see from the figure on the right-hand side of this slide, our measurements of, we can make measurements of airflow velocity, we can look at heat transfer, we can look at the fuel decomposition, all in this lab in exactly the same way that we're doing in the field. So that gives us a really good opportunity to relate very closely our lab work with the field work. And that is something that I think is relatively unique to this project, and to the amount of quantification of the field experiments that we have really lets us check whether we're getting the right conditions in the lab and the right kind of fire behaviors. And it's not perfect, and it doesn't always work, but at least we're able to figure out how close we are and how good of a job we're doing in matching this. So the other advantage we have in the lab is, if I just take some examples of some field measurement data, which are the three plots arranged vertically on the left-hand side of this slide, and let you kind of just give you an idea of what we do with that sort of data in the lab. So the plots on the left-hand side are measuring air temperature at the top, and the orange and the green and the blue are wind speed components in the vertical or the horizontal direction. And you can see that this is data taken from a real fire, one of our real burns, and it's all over the place. We've got spikes in temperature, we've got spikes in velocity, and we can't really ever control this. So that means, between one burn and the next in the field, we can have quite different behaviors arising from these conditions. But if we go to the lab, which are the three images on the right-hand side, we can control that much, much better. So we can, for example, set the air temperature to be 40 degrees Celsius and hold it constant at that condition. And that means we can study what the fire behavior is like, how the fuel is burning, what the flow through the fuel bed is doing at that temperature. We can break it all down and really study it at that one condition. Same with the wind speed. So for example, here I've set the vertical wind to be 0, but the horizontal wind, which is the blue line, to be a constant 4 meters per second. And that's a condition that we can produce in the lab time and time again, and really systematically study the other variables whilst we keep that wind speed constant. And that's a huge advantage of working in the lab. We can do that. Of course, if we want to apply these measurements, we have to understand how all of the variability and how all of the uncertainty that we measure in the field impacts on these measurements. But we have ways of doing that and ways of building that complexity back into our understanding. So that's kind of why we like working in the lab. We can simplify the problem to the level where we can really begin to systematically change variables and really understand how individual parameters impact on the fire behavior. So just to give you an insight into our world, I guess, this is just a bit of a panorama of the Edinburgh Fire Lab. I've not managed to quite capture everything that we do here, but you'll see a few other pieces of apparatus as we go through the presentation. But the first thing that we go from left to right of this image, sorry for all of the arrows, it's almost more arrows than image, but if you go from left to right, then I'll just walk you through what we can do. So on the left-hand side, reading off the top row, this is a piece of apparatus that really lets us control to a very high degree the thermal exposure that we can apply to some vegetation. So it's a piece of apparatus you can see on the bottom of the image called the fire propagation apparatus. It's a standardized piece of apparatus that's used a lot in fire protection engineering. So that's looking at fire safety in buildings and so on. But we can modify it, we can adapt it, and we can use it to really understand how vegetation will ignite. Once it ignites, how it burns, and once it burns, how much energy is released, and all sorts of things. So that's a really great tool for us, and that lets us measure fuel flammability. Okay, so it lets us quantify how easy it is to ignite something, and how that thing will then burn, how that vegetation will burn, how much energy it will release, and so on. So that's really great for us. Moving again to the right, we've got combustion product analysis. So, one of the things that we see a lot in wildfires is a transition, for example, from a flaming fire to a smouldering fire, and how fuels under different conditions will spread flame and spread smouldering fire is really kind of interesting to know from an air quality issue, but also from a risk management perspective as well. So by analyzing the combustion products, we can get some insight into that behavior at the lab scale. That's a really powerful diagnostic. It also lets us understand something about the combustion processes that are going on as a fuel burns. Moving further to the right, we've got a space where we can analyze flame spread and energy release. We call that the large calorimeter, and we will show some results from experiments in that space just in the next couple of slides. And finally, we can measure energy release also through another standardized piece of apparatus called the cone calorimeter. So again, that gives us a nice control of the thermal exposure and lets us understand how much energy is being released as a fuel burns, and we can change the condition of that vegetation. We can burn with high bulk densities, with low bulk densities, with high moisture content, with low moisture content, and really understand how each of these variables changes the burning behavior. So that's what it looks like in our lab. It's not a very tidy lab, you can maybe see from that picture, but it's a very functional lab, and we're really grateful to be able to use that space. So moving on, I'm just going to break down the problem even more, I think. So I showed you this image on the left already. This is our flame spread table, and as I said previously, we can measure airflow, heat transfer, fuel decomposition using this apparatus, and we can relate that back to the field experiments. But the one advantage this has is that we can really rapidly manipulate things like the fuel load. So what is the bulk density of fuel that we're interested in? We can really easily change the fuel structure. So, do we have a densely packed fuel bed, or is it slightly more permeable? And we can also change the fuel moisture because we can precondition fuels before burning them. So that's a really great diagnostic. But basically, all that lets us do is to take a field experiment and run something similar in our lab. What we're trying to understand here, as I mentioned before, is we're trying to get really to the heart of those fire processes. Really to understand what fundamental phenomena govern this flame spread. And that's really important because we want to try and understand a little bit about how we can predict the fire behavior better. And that'll kind of emerge in the next few slides. But if we break the problem down, we've got the airflow, the heat transfer, and the fuel decomposition. We can further study each of these in a separate piece of apparatus. The first one is basically we can vary the speed and temperature of an airflow that's flowing through a porous fuel bed. So this is an apparatus that we'll see in more detail later on. It's called the Wildland Exposure Ignition Response Device, or the WEIRD for short. And it's a great tool that lets us look at how fuel beds and how litter layers in particular, and eventually shrubs and so on, how they change and alter the airflow around them during a fire. We can then go to study the heat transfer processes, so we can look at how does, if we've got a lot of preheating of the fuel due to the flames, or if we've got less preheating of the fuel due to the flames, we can take a look at how that changes the thermal environment and how the fuels respond to that. How does different vegetation under different conditions respond to heating from a simulated advancing flame front in different ways. And that's this kind of middle image on the right-hand side. That's using the fire propagation apparatus I mentioned before. and that's giving a good overview of the flammability of these fuels. Going even more into kind of the details of this, we can take a look at the fuel decomposition. So this kind of circular device is the carousel for loading samples into a piece of apparatus called a thermogravimetric analyzer, which is basically a fancy piece of kit that lets you change the temperature that you heat a sample to and measure how that sample responds. And that means, we can heat things at a high heating rate or at a low heating rate, and by measuring the weight of a sample, we can look at how it responds, and we can understand from that a little bit about the chemistry. So we can see, for example, do pine needles have a different type of response to some kind of other leaf, to an oak leaf or something like that. We can look at a really fundamental level at the fuel composition and how that changes the fire processes. So going through each one of these in detail, and I've put little mugshots of the responsible person on these slides. So this is work that Zach is kind of leading in the team, and he's leading the work on what we're calling the table, which allows us to reproduce some of those field scale burns in the lab. And the table is actually a very simple apparatus, but with it, it brings a lot of complexity. But basically what we can do is change fuel loadings, change bulk densities, change fuel structure on this table, ignite it in a very consistent way, and really remove the effects of ambient wind, moisture content, and so on while studying the problem. So it lets us just make the problem a little bit simpler, so that when we make the measurements, it's a little easier to relate things to each other. And one of the great things that we've been able to do with this, we've got 3 measurement stations. So we can measure temperatures, we can measure flows, we can measure heat fluxes, we can measure the total amount of energy that's being released from the fire at any time using these diagnostics. And here's a really, I think, powerful visual image of the kind of things we can explore. And this is this is work that has been done before, but this is our approach to it, and I'll show you in the next slide some of the additional insights we're getting on what's been done before. So just walking through this image, this is a composite image made of from 4 different times during one experiment, and the fuel layer across the table was varied. So on the left-hand side, we've got a fuel loading of 1.6 kilograms per meter squared. That decreases as we move to the right-hand side. And what we're able to do on the table here is look at that fuel loading, what is the flame height. So in the case of the left-hand side of this image, the flame height is about 0.9 meters. The heat release rate, so the amount of energy being given off by the fire at this time, is on the order of 50 kilowatts. Now, as we move to the right-hand side of this image, we've reduced the fuel load. And for example, once we get down to a fuel load of 1/4 of the 1.6 kilograms per meter squared, so this is the 3rd panel along from the left, we can see that the flame height has reduced to 0.3 meters. The heat release rate is much lower, 16 kilowatts compared to 50 kilowatts. So, these sorts of things are very simple but very powerful, I think, images to understand the effect of the fuel loading on the fire behavior and what the fire looks like. But beyond that, we're able to go kind of one step further. As I said before, that kind of work has been done before at the lab scale. The thing that's kind of new in this project is we're instrumenting these experiments in order to really get into the details of the driving processes behind the fire behavior. So this slide has got 2 plots on it. So on the left-hand side is a plot I grabbed of some flow velocity within the fuel layer. And the flow velocities, as you can see in the plot on the left-hand side, they start off around 0 and a little bit negative in general. But as time advances, and once we get to time equals 0 on the x-axis, we see that we have this flow reversal, and the flow goes from being negative to positive, and also changes in magnitude quite a lot. Well, time equals 0 is the arrival of the flame front. So what we're really seeing here is getting some insight into how the flows through the fuel layer change as a function of the position of the flame front, and that's really important information that we can augment the field work with. On the right-hand side of this plot, we're measuring the heat flux. So this is the total heat flux being received at the bottom of the fuel layer on this table. As we said before, we're not really at the position yet to make definitive statements about any of this, but we can see that we have heat fluxes ranging from 70 kilowatts per square meter down to maybe 30 kilowatts per square meter. And that's really interesting because that helps us to put bounds on the work and really to integrate with the rest of the team, and particularly with the work that Bob has been doing at the field scale around the heat fluxes that are coming off of these low-intensity fires. So these are really details that are kind of one level down from most of what we would see at this scale. So that's a really neat contribution. But building on that, and we've got those heat flux measurements, well, we can reproduce them in the lab using the fire propagation apparatus. And this is what the work that Carlos has been doing is to try and relate measurements of heat flux to fire behavior. And particularly the flammability of different fuels. So the picture on the top right-hand side here, we've got three little baskets of pine needles that have been treated in different ways. So, for example, the pine needles on the left-hand side have been ground and kind of powdered, if you like, and that changes obviously the structure and the permeability of that fuel layer. It doesn't necessarily mean it has any bearing on what you might find in the field, but it puts a very strict bound on the result. We've got different conditions on those other pine needles in the other two baskets as well. And we can ignite these under very controlled conditions and look at the burning behavior of these. Look at how the structure of the pine needles changes, how the fuel burns. Look at how the airflow availability changes, the amount of energy that's released as these fuels burn, and really get a good handle on all these parameters. Going further beyond that, because here we've already mentioned the structure of the fuel, I think one of the things that is also important is to understand. Oops, sorry, I'm getting ahead of myself. I'm just going to back up a little bit. From doing these sorts of studies, we can look at the ignition of the fuel and how easy the fuels are to ignite. So by manipulating the magnitude of the applied heating to the fuel, we can construct plots like you see on this slide. And if we just look only at the blue line we're going to read off on the right-hand axis, so the axis that goes from 0 to 400. And the blue line is the time it takes for the sample to ignite when it's exposed to different heat fluxes. So a heat flux of 15 kilowatts per square meter, the sample will ignite in about 350 seconds. So that's quite a long time for that sample to ignite at that kind of level of heat flux. But as we increase the intensity of the heat flux up to 30 kilowatts per square meter, if we read off this blue curve, the time to ignition is something much closer to 20 seconds. So this is a really powerful tool to understand how the heat flux and how the magnitude of that external heating is going to impact the ignition of these forest fuels. And we can do this again because it's in the lab and we're using small samples. We can do many of these in a relatively short space of time and look at the different fuel conditions, the different fuel structures, and so on. The other part of the work that Carlos has been doing is to understand how these fuels behave on a very fundamental level. So on the level of the of kind of less than one pine needle, I would say. So these experiments are run using something called a thermogravimetric analyzer, which I mentioned before. And if you look at the kind of solid orange curve on this, what we're seeing is the rate at which the sample is losing mass, the rate at which it is undergoing thermal decomposition as a function of temperature. And that's really, really useful data to understand how the fuels respond when they're heated. So, in this one we see a huge peak at temperatures of something around 350 Celsius. We see a huge peak there in the rate of mass loss, and then that decreases, and we have this second peak at around 500 degrees Celsius as well. And that tells us something about how the fuel is decomposing thermally, and also how the char oxidation or the smoldering of that fuel, how that behaves as well. So these sorts of really detailed measurements, they let us relate the small-scale experiments to the fundamental, chemical and physical processes going on in the fuel. Now, moving on from that, now we've got the chemistry kind of tied down a little bit. Obviously, we need to get the air and the oxygen from the air to mix with any of the products of the fuel decomposition. and we understand the airflow processes. We're delving into that a little bit using the WEIRD, which I mentioned before. And the WEIRD is a very simple device kind of conceptually, but how it operates is maybe not quite so straightforward. But basically, we have, I'm not sure this will show up super clearly, but this big section in the middle underneath the laptop is a wind tunnel. And at the left-hand end of the wind tunnel, the airflow that we're providing goes through a heater, and we can heat this airflow up to really high temperatures, not quite up to the the 1000 or 1200 Celsius of a flame, but we can get pretty close to that, and we can put that flow and push that flow through various fuel beds or representative fuel beds. So at the minute here, it's full of needles that are taken from the plantation at Silas Little. And these are experiments that let us understand how the air moves through these pine needles and how the structure of the fuel bed, the density of the fuel bed, and so on will change that airflow. And that's really important if we want to understand how the fuel is heated ahead of the flame front. It's really important if we want to understand how smoldering can happen in the fuel layer as well. So these are great little experiments that we're running, and this is kind of a really nice new step that we've been able to do with this project. And some of the preliminary data here that we've got is looking at the pressure drop in pitch pine beds of different flow velocities. So we can see here that we're getting data already that's coming out of this that's really helping us to understand the fundamental processes of the fire spread. So, ultimately, the end goal of all of this is to better understand the fire spread, so that we can have improved physics-based fire models. And I think that's something that runs throughout this work, and that I want to emphasize. And what we're able to do at this point is to understand which of the processes that we're studying at the lab scale are relevant in the model, which ones the models are capturing well, and which ones some of these fire models aren't capturing so well. And in doing so, we're able to propose how to develop the model. We're able to propose ways in which we can improve the accuracy of these modeling activities. So that's kind of the context that fits into. It's nice to know all this stuff, but we have to have an end result for it, and the end result here is the high-resolution computer simulations. So, what we're doing just in terms of this work is, I've walked you through, I think, hopefully, in a slightly logical way, some of the steps that we take to go from the field work and to learn from that. So we start off at the field. We then jump down, I guess, to the lab scale flame spread. And from there, we can do detailed study of the fire processes. And from there, we can input this data into the development of fire spread models. But the thing that I think is great about this project is that once we've done all of that, we then go through the loop again. We then go back to the field work, taking all of the things that we've learned from the lab scale and from the modeling. We go back to the field work, and we check out how did we do. And the way that this project is structured that makes it really neat is that we can go through this loop several times, varying whatever parameters that we become interested in or that we think are relevant, and to really get the best out of this. So I think that's something that's really nice about this project, and hopefully in the next few years we will be in a much better position than we are now in terms of our understanding of some of these detailed processes that govern the fire behaviour. So I hope that made sense. I hope that was an interesting presentation, and I guess I'll wrap up now and pass back to Amanda for any questions.
All right, excellent. Thank you so much. Wow. Yeah, so again, if folks have questions, please feel free to type them into the chat box. I think with this number of participants, we'll be able to open up the phone lines, but I'd like to start with any questions that are in the chat box. I kind of have one to get you started. So in watching your presentation, it feels like we were transported across the big pond and given an up-close tour of your fire lab. So first of all, thank you for that. And then building on that, it's really nice to be able to compare what you studied in the lab environment to what you've seen in the field environment. My question is, have you had any kind of aha moments from studying the fire dynamics in both the lab and the field?
Almost every time we do something, there's an aha moment at that scale. I mean, it's really great to be able to work in the field, because that really lets us, push us out of our comfort zone. Most of us here in Edinburgh, we come from an engineering background, and when we get transported over into, into more of a forestry or ecology or remote sensing background, like we do with the team in the field, we learn a lot every single time that we do that. So, I mean, that's one of the biggest aha moments, is every time we go over, we learn something new about fuels, we learn something new about the specific ecosystem there, and we learn something new about the fire behaviors that we can see, and even really seeing things at the field scale that you never see in the lab. So, just for example, burning in the morning versus burning in the evening. Burning at noon versus burning later in the afternoon. The changes in humidity and the environmental conditions really are great to see how the fire behavior is really sensitive to these things. And that's something that, as researchers in a lab, we never get to see. But by being able to get out into the field and understand this, you get a much better sense of what are the important variables to study and what are the the interesting factors. And there's a lot of knowledge in the team out there and with the Forest Fire Service. So being able to pick their brains about the fire behavior and what affects it is invaluable to us.
Excellent, thank you. I'm not seeing questions in the chat box so far. What I think I'm going to do, since we have a good-sized group, I'm going to unmute the phone line. So what I'm going to ask, wait, we have a question. All right, I'm going to wait on unmuting the phone line. So one question that came in says, this is cool. Looks like a perfect tool for isolating individual factor or process. What would be missing from the lab experiment compared to idealized simulations? Interactions. Suppose your conditions are fixed during the experiment. Can you put a simple terrain into your table? Good question.
Yeah, that's a great question. Thank you very much for that one. So absolutely, I mean, this is one of the kind of strengths and also it's the weakness of lab experiments, which is we can have lots of control over all these individual factors, and that makes studying them many, many times simpler often than in the field. And how do you reintroduce that complexity is a really big part of this. And one part of that is addressed, or will be addressed in the next seminar actually by the guys at WPI and Notre Dame on this, which they're going to talk about how they use a wind tunnel to understand some of these things. And that directly introduces the effect of an external wind on the fire behavior. So again, as part of the project team, that's kind of our development in terms of we're quite fundamental and quite process driven in Edinburgh, and we kind of dial that up into larger scale experiments in the lab at WPI and also the fieldwork. We can obviously, as the project evolves, we'll be looking at introducing more of the complexity and pushing ourselves much harder on what we understand and how we understand it by doing exactly the kind of things that are suggested, looking at the effects of potentially terrain, looking at the effects of combining multiple parameters on the spread table and in the other pieces of apparatus as well. So yeah, absolutely, lots we can do here, and every time we add something new to the list, we just think of a new PhD project and a new master's project, and it's a really great problem for doing that.
Great, thank you. We'll give folks another moment to pop a question into the chat box. But I'll also say I'd like to open up the phone line. So in the meantime, if you can mute your own phone line, unless you've got a question ready. All right. I don't see any other questions in the chat box, so I'm going to unmute the phone line. All right, the phone lines are unmuted. So if you have a question, please feel free to ask Dr. Hadden.
It was a good presentation. Yeah. If you want to. Are you muted there? Yeah.
Do we have a question? Or is that background noise? Aha. Oh, let's see. Oh, Ken Clark has a question. He's typing.
Unmuted. I don't think it was muted.
Somebody is unmuted, and you can feel free to ask your question. Do you have a question?
Hey, this is Mike Gallagher. I just want to say, really nice presentation, guys, and it really ties everything together. I'm really excited about some of your results, and I was just up in another portion of this project is a wind tunnel that's in Massachusetts, and it was nice to see some of your data presented there. I think that there's some things that are going on at sort of a medium scale between what Rory presented for Edinburgh and the Pine Barrens here, where the data that you guys are collecting right now, I think, will really nicely guide some of these intermediate scale experiments. Yeah, so I guess that's more of a comment, but just really nice work.
Yeah, sweet. Thanks, Mike. I mean, just for others on the call, I mean, that is, I think, a really great strength of this project is being able to, to feed the data across the different scales, physical scales of the experiment, and also between the research team. It's a really good way, to study almost the entire problem. I wouldn't say we fixed, we're going to be able to address every issue and touch on every issue, but that for me is what keeps this project exciting.
Very cool. Other questions? I see Ken Clark had a comment. He says, great talk. Thank you for clarifying a number of questions. A number of results are consistent across scales, which is exciting. That's from Ken.
Always good to be consistent. I mean, that's great. Thanks, Ken, for that.
Excellent. Other folks on the line, questions?
So I think we have a lot more to talk about. I think once since we're working on this together offline, as far as next steps and different fuel types, for instance, adding oak leaves or looking at something like oak leaves, or these are different species, and some additional materials. So, we're actually in the process of talking about that right now. I'm not sure if everybody on. Well, I guess it's mostly the project that's here. but yeah, looking at some different fuels and kind of picking ones that are both here in the Pine Barrens, but that are also represented across a broader range of the Atlantic coastal plain and the eastern fire adapted ecosystems. So I think as this unfolds, there's relevance to this in a lot of different places. Both in a fundamental sort of way, but then also in an applied management context. So moving forward, I'm looking forward to the continuation of this. I mean, it's so neat just comparing pine needles, different amounts of pine needles, but looking at different species, I think is going to be really exciting too. And we'll kind of inform some of the ecological patterns that we probably have seen for a long time. So, again, just another angle on that there.
Yeah, absolutely. I mean, that's great. I think we are, as you said, Mike, we're kind of at the early stages of this, and there's, there are a lot more to do as the research develops and as the ideas kind of keep coming and the application space hopefully widens out a little bit. But it is great to have all this infrastructure in place through this project that lets us relatively rapidly change our focus and shift our ideas and try out different things using different fuels, for example, and trying to capture some of that stuff. So I think it's great.
Hey, Rory, this is Warren Heilman. Got a question for you on the, the airflow through your fuels. Are you finding that the measured flow to be relatively smoothly varying, or is there, a stochastic nature to that flow?
Thanks, Warren. That's a great question. Do you know what? I don't know the answer to that. I know that Eric's online somewhere. He's right on top of all of that data, but I'm not going to throw him under the bus right now in terms of making him pipe up on that question. But I know that we are right now, if I just get back a couple of slides, using the wind tunnel here, we are kind of right in the process right now of trying to characterize that stuff across a range of the conditions. And we've been working on this quite a lot in the last, I would say, maybe 2 weeks. This has been really up and going and working well. So we are in the early days of this stuff. But as soon as we know anything kind of useful, we'll for sure make sure we get that out into the rest of the team. Right now, the kind of plots I'm showing right now, if you can see them, the kind of pressure drop as a function of distance through the fuel bed is kind of where we are with this stuff. So yeah, we'll get there eventually. But great question, and yeah, we don't know yet, I guess, is the answer.
Okay, yeah, thanks.
Awesome. I think we have time for another question, maybe one more if anybody has one. This is your chance. All right. Well, I suppose we can wrap up. Thanks everybody so much for joining us. Thank you, Dr. Hadden, for that excellent presentation. This webinar has been recorded, and we will post it on the North Atlantic Fire Science Exchange website. Thanks again for joining us, and feel free to give us a shout if you have any questions, concerns, ideas for future webinars or discussion. Thank you.
And thank you so much, Rory. Everybody. Thank you. Thank you, Amanda. Thanks, guys.